Pressure is force over area. It has units of newtons per metre squared. The question we will look at in connection with ideal gases is what causes this force. The area part of pressure is fairly easy to get a grip on. The area of force is the area onto which you are applying a force. It has a two-dimensional shape with an expression of area. For a square or rectangle, the area is given as width times height. For a circle, it is pi r squared. For a triangle, it is half base times height. All two-dimensional shapes have an expression for their area. But for the purposes of an ideal gas, we will use a square, width times height. We do this so that we can construct a cube later in which to derive our kinetic equations for an ideal gas. But not now. For now, we stick to the general idea of pressure. Back to our question. What causes the force of an ideal gas? The force of an ideal gas should be familiar to anyone who studied simple mechanics. The force generated by an ideal gas is caused by the collision of the ideal gas with the walls of its container. If the ideal gas collides perpendicularly to the wall of the container, then it will exert a force equal to the mass of the ideal gas particle times the change in acceleration of that particle. As an ideal gas doesn't lose energy on collisions, then the force must be equal to twice the mass of the gas times the acceleration of the gas towards the wall of the container. If you remember the podcast on momentum conservation, then you should be able to understand this. The change in force is equal to the change in acceleration times mass. The mass doesn't change on collision. Both energy, because the objects don't change the form of the energy, and momentum are conserved within the collision. So the spread of the gas doesn't change. The speed of the gas doesn't change. It merely changes direction. This change in direction means that the velocity, and therefore the acceleration of the gas particle, does change. Equal magnitude and opposite direction. Okay, so far you are thinking to yourselves, surely that means the velocities cancel each other out, and we have no force then. But here you've forgotten that Newton's second law actually says, the change in force is equal to the mass of an object times the change in acceleration. The change in acceleration is equal to the final acceleration minus the initial acceleration. If we take our initial acceleration as positive, then our final acceleration must be negative. It's only changed direction. Therefore, negative acceleration minus positive acceleration equals twice negative acceleration. That's strange. Surely that means that we have negative force on the wall then. Actually, you're wrong again here. We have only been referring to the gas particle so far. If we refer to the wall, then we must use Newton's third law to tell us the relationship. For every action, there is an equal and opposite reaction. This means that the force on the wall is equal in magnitude to the force on the gas, but opposite in direction. The force in our pressure equation is equal to twice the mass of the gas particle times the acceleration of the gas particle. As I said, this will be covered in more detail when we discuss the kinetic properties of the ideal gas in future podcasts.